please let us know. Maybe actually I can start off if no one else is ready. One question I was wondering, so for usual Weil-Cell metals, we know that one way of understanding it is by taking a 2D cut of the 3D momentum space, and that looks like a Chern insulator. Or at least if you're in between the two Weil nodes. Is there some analogous statement for your system?
Yeah, I mean, yes. So I think the main difference, and sorry, I stopped sharing screen, but maybe I'll put a picture back up here if you don't mind. So yeah, it's basically, yes. I mean, it's basically like that, except you've got two branches. So, you know, these sort of branches, you know, where you take your, so let's start with the Weil dipole case, right? So if I erase the red ones and I had a blue one and a red one, right? And then you see this Fermi arc because, you know, you have this line connecting the plus and the minus, the positive and negative chirality Weil node. So that story is not so different here. It's just that when you take this cut, you actually get two branches, right? So it's more so it's not a net sort of charge. You get these two branches at different momenta.
So are you imagining slicing parallel to one of the? So how are you imagining slicing this cross?
Right. So you know, right. So if I cut, you know, if I cut between the origin here and one of these red ones, right? So now I've come through one of the sources. So here I'm going to see sort of one, you know, I'm only going to see one branch like this one here, right? So it'll depend on the cut, right? So but for some cuts you are just going to see, because yeah, so there's sort of, you know, a cut over here where you get one chirality, right? But then on the cut, if you take a same cut at a different value at the opposite value of kx, you're going to get the opposite chirality. And again, if you yeah, does that answer your question?
Yeah, I think so. I'll try to visualize it a bit more later, but that helps. Thank you. I see also we have a few raised hands. Maybe Mengcheng.
Hey, so I have a question for Sheng-Jie. So you mentioned
yes.
intrinsically quasi-crystalline SPT phases, right? Obviously, they're very interesting, but I just want to ask, you know, why there are no intrinsic periodic phases for the ordinary system. Like in terms of I can probably also, you know, write elasticity theory for ordinary crystals in terms of these theta fields. And what stops these terms from appearing in an ordinary crystal?
No, I think in the ordinary crystals, you don't have enough elastic modes to write out these terms. We can write out these terms because we have more these theta fields, so that these terms appear.
The number of theta fields is greater than the spatial dimension, these terms can appear. Is that?
Yeah.
I see. Okay. All right. Thank you.
I think Dominic had his hand raised.
Yeah, so I just wanted to ask Fiona, just to clarify, you're not saying that these theories can only occur of a boundary of something else. You're saying that if you want over emergence images to be realized microscopically, then you must be at the boundary of something else. Is that the statement?
Well, okay. Are you asking about the fermionic system?
Well, does it matter?
Well, okay. I mean, because I assume the comment is coming from this fact that there's this Villain model formulation with the Hoped anomalies. Is that what you're like in the context of the fermionic model, right? The fermionic downstructure that I wrote down just doesn't have a closed. does not have a closed Fermi surface in 2D, and you can show very easily that if you close the Fermi surface, that all of these anomalies are, you know, are not there. However, is there some abstract, you know, is there some realization of this anomaly? You know, I mean, that's a different question. Is that what you're asking?
I mean, so, well, I mean, let's talk about the bosonic things, which I maybe understand better. That there, it's an anomaly between the
Yes.
and some of those symmetries, you know, maybe that are anomalous, maybe emergent symmetries. So if you want to have a lattice model that doesn't have those symmetries realized microscopically, then there's no problem, right?
Right. Yeah. So indeed, the plaquette icing model. Sorry, I just want to say the plaquette XY model is, you know, is perfectly fine in 2D, but it doesn't have both symmetries. Yeah. But and more generally, right? I mean, you know, you can. It's perfectly fine. You know, the momentum currents are not necessarily ones that we typically believe, you know, have to be conserved in the presence of electric fields. So in that sense, you might think, you know, there's nothing fundamental about the anomaly that prevents it from being realized. But the particular free fermion model that I described, you know, does not exist in 2 dimensions, right? Like, you know, if you once you put it on a Brillouin zone, you have to bring those bands back down. You have to get another. You have to close the Fermi surface. There's no way around that.
All right. Thanks.
Syed, if I say that correctly, please
Yes.
go ahead.
Yeah, I have a question for each one of the speakers. So I have 2 questions. Question number 1 for first speaker is that let's say I'm introducing this quasi-crystallinity as a defect, so perturbatively. So let's say I'm starting from the TI and slowly deform my crystal. How the classification would change, or what are the main effect of the in terms of the classification with the strong symmetries?
You mean you slightly deform the quasi-crystals?
Yes. I mean, start from the regular TI and slowly add quasi-crystallinity to it as a defect.
Oh, starting from usual TI.
Yes. So let's say start from time reversal symmetric TI.
My guess would be it will stay in the same TI phase.
So it doesn't have any specific boundary, you know, effect or response effect.
Are you asking about a strong TI?
Yes, a strong TI.
Yeah, strong TI doesn't care about whether you're crystal or quasi-crystal or anything. I mean, I mean, that structure is not important. That's why it's called strong.
So what I'm saying that, okay, so quasi-crystallinity essentially doesn't change the strong phases.
Yeah.
Okay. All right. So another question is for the second talk is that you shown magnetic flux in the quadruple wild case, and in the regular, at least for regular wild cases, we know that when you add the magnetic flux, then it's proportional to the length of the Fermi arcs. Do you see also the same phenomena here? I think you're muted.
Sorry, I muted myself. Yes, right. So this is something that I glossed over just for the sake of time, but indeed, there is some constant, right? Which, so in the 2D theory, you can think of it as almost a cutoff, like how far out do you extend these things? But of course, it's not, it's not an energy cutoff, it's just a momentum cutoff, and those are not the same thing. But yes, it's the position of the bulk file nodes, and that is, of course, going to affect the magnitude of these surface responses. And yes, and then now
yes, so it still is going to be proportional to the particular length of the Fermi arcs on the surface, that charge response.
So that's right. Yeah, when you look at anything, within the surface theory, these responses do care about the, and similarly, you know, the bulk response. So the quadrupole, I mean, in the bulk response, the place where the separation between the vial nodes is hidden, right, is in this quadrupole moment, right? Which, so if I take my configuration and I just like stretch it out, you know, that I take K to like lambda times K, that's going to scale everything by lambda squared, right? So in this case, these quadrupolar things don't scale linearly, but quadratically with that scale of momentum.
I see. Thank you.
Masaki, please go ahead.
Yeah, I have question to Fiona. Thanks for nice talk. So if I understand correctly, you consider the KX, KY type dispersion relation in 2D Brillouin zone, at least near the origin. And of course, it cannot be realized in purely 2D system without other singularity. So you construct it on the surface of 3D while semi-metal. So my question is, if we come up with even more crazier dispersion into the like KX cubed or whatever, can you always realize this on the surface of 3D, or maybe sometimes you need 4D, or even in any dimension you cannot realize some dispersion? Do you have any idea, comment?
I mean, that's a really interesting question. It's not one that I've thought about very much. You know, certainly, if you go up a dimension and you think about so you know, yeah, if I mean, and the thing that's not, I mean, so I think your hint, right, is, I mean, if it's appropriate to be, in as much as it's appropriate to be guided by what we know from thinking about like these higher rank theories as sort of describing these, you know, maybe subleading mixed anomalies that might be relevant to the lattice, you know, so then in 2 dimensions, like, you know, what there's sort of nothing interesting beyond rank 2. And I think, you know, one way to think about that in the context of the band theory is there's some, you know, there's some notion of like a quadrupolar something, you know, so for higher order topological insulators have a polarization, higher order topological insulators have a quadrupolarization. And in 2D, you know, that's where it stops. If you go up to 3D, you can start talking about octopole moments. So in 2D, I mean, I certainly don't, and your question about, you know, things being realized, you know, only at the boundaries of 4D systems, that is, I mean, and if anyone else wants to comment on that, I'd be very interested in hearing. I just don't know. But my suspicion is that in 2D, you know, there's nothing obvious in 2D beyond this, but in 3D, you know, you might think quadrupole and then, you know, octopole. And same thing that, you know, if you look at the available higher rank theories, you have another kind of layer there.
Yeah, thanks very much.
Zen has his hand raised.
I have a question for Fiona. So the standard move for anomaly inflow is that you have a normal system in D dimension, and then it's cancelled by a gapped system in D+1, right? So here you are saying your anomalous fermi is actually cancelled by a wild semi-metal. So I'm wondering whether it's special about this anomaly, or can you find a gap 3D system that have this 2D surface of this crossing Fermi surface?
The crossing Fermi surface, no. Although there is a 3D system. So actually in the context of, I mean, and Taylor like alluded to this in his talk, but I think he didn't spend very much time on it. But if you go to, you know, higher order topological insulators, there is a field theory that's similar to this. It's different in the sense that here, you know, we really have the electromagnetic field and we have the lattice field. And so we're really seeing this mixed anomaly. In the field theory that we wrote down for the higher order topological insulators, you know, it seemed like it just wanted to be 2 copies of the lattice theory, but my guess is that there's, you know, I mean, basically that if you took 2 copies of that theory, right? So there is a bulk field theory that for which the surface state is that cancels the anomaly of this XY plaquette model. And I think it's in, I think it's mentioned in one of the papers by Nadia and Xu Heng. Maybe they're
regardless of the XY plaquette model, I'm just wondering about the fermion model you design. So the
right. So if you really want these sort of you know, Fermi arcs like crossing the whole surface, then you know, so the problem is you start with this and then you grow them, but you know, when they come together, then you have other points like this, right? So that's sort of exactly at the point where the bulk nodes touch, right? Then so that and even then it's a little I mean,
so I guess it's a kind of an answer to Masaki's question. So your system, your 3+1D bulk is still a gapless system.
Yeah.
As a boundary of a 4+1D system. So if you want to find the exactly gap,
if you want the gap system, yeah.
Actually, you have to raise 2 dimensions to get a gap bulk.
Yeah, that's an interesting point. I mean, you know, it's like the same. It's the same thing with an ordinary vial semi-metal, right? That we have this like charge anomaly on the surface that's canceled by this gapless 3D bulk. Why? Because you know the bulk, you have to actually get charge from the top to the bottom surface. But yes, that's a very interesting point.
Yeah, so a Fermi arc is not just a 't Hooft anomaly.
Right.
It's actually it's a worse kind of anomaly. It's not just an anomaly; it's an inconsistent anomaly.
Right.
If that makes any sense. That's why you need a gapless variant in the bulk.
Yeah, so here, right. So from that point of view here, it's less clear. Because this is, yeah. Maybe someone else wants to comment on that, but.
Are there any other questions? Syed raised his hand again.
Yes. Just a quick question. Is this scenario of the quadruple wire can be generalized to the case of superconducting system? Because I'm aware of one work from Sato group in Japan at PRO 2015. They have Majorana crust Fermi arcs, which is it's a superconducting wire semi-metal. So I don't know if it's easy to generalize this whole thing.
I mean, okay, so there's 2 separate questions. One is, you know, could you imagine imposing a symmetry, for example, such that the dipole moment of the vial nodes has to vanish and the leading contribution is quadrupolar? Sure, yeah. I mean, the nature of the response, you know, because they're because it's a superconductor, yeah, maybe I
think probably
don't want
the
to
question
comment.
is that mostly is that this crust band is really that important by itself, or you need more than just the crust band on the surface?
So I would say that the important feature in the bulk is the fact that if you look at these vial nodes, right, you can define a dipole moment, right? So think of your vial nodes as point charges, right? They have, you know, charge +1 or -1, depending on whether they're sources or sinks of Berry curvature, right? And then from that configuration, you can calculate. So we know that the total charge has to vanish, right? For a vial semi-metal, you can then calculate its dipole moment and its quadrupole moment. And so from the point of view of the bulk response theory, the important thing is just that the dipole moment vanishes and the leading term is this quadrupole moment, which is non-vanishing. And you know, the kind of these interesting features of sort of coupling charge response to lattice response just results from that.
Great. I have maybe a question for Sheng-Jie. So you kind of hinted it already on your conclusion slides, but do you have a sense of how hard or easy it would be to write down a lattice model? In particular, does your field theory analysis give any indication of how you would try to construct such a model, or is it a complete open question? For these intrinsically quasi-crystal SPTs?
Yeah, I think it's pretty open. But if you remember, I talked about this quasi translation, transcendent quasi symmetries or quasi periodicity. It's a condition on a Hamiltonian parameterized by this theta. And maybe you can start to consider some local terms that act on, locally in space and satisfy the conditions, and try to write out some models along this line. Maybe, yeah.
It'll be very interesting.
Yeah.
Any other questions for either of the speakers? Okay, I don't see any hands. So if not, let me also, just like Fiona, take the opportunity to thank all the organizers for the very nice workshop. I don't know if maybe one of the organizers wants to, say something to wrap things up, or.
Yeah, well, I'll just conclude. So we obviously want to thank everybody for participating. We had to put talks short in order to not take up too much people's time, but we wanted to allow plenty of time for discussion, and you all fulfill your end of the bargain in terms of asking lots of good questions to fill that time up. So that was great. And then we also should thank the Simons Center staff, like Janelle Rogers. I don't know if they're listening, but they were very helpful in dealing with all the stuff, and we had to reschedule the workshop and change it to virtual and make last minute changes. So she was very helpful with all of that. And then, so if you want to continue the discussions, well, I think we don't want to keep this Zoom open, but you can move to the Discord if you like, if you want to keep talking about any of the questions that arose today or throughout the workshop. All right, so yeah, thanks everyone.